Okay, so far we have obtained the Bose-Einstein distribution function as well as the Fermi-Dirac distribution function. So we shall follow the same procedure to obtain the classical distribution function known as the Maxell Boltzmann distribution function. So as usual, we here we start with the number of accessible microstates for a system which is classical, WMB. So WMB corresponding to the distribution set Ni, that is given by as usual pi over I Ga raised to Ni Gi raised to Ni divided by Ni factorial. So this is the starting step for all the things. So let me call it as equation number 1. Then okay, therefore I can say log of W is equal to, I'm not going for any more explanations, it's all self-explanatory, sum over I Ni log Ni log Gi minus log of Ni factorial. Okay, so that is the thing. So which can be expanded by using Stirling's method, that is sum over I Ni log Gi. So there is no scope for an expansion there. There should be a factorial. That is, second one is Ni log Ni plus Ni. It will become minus, will become plus. So let's, therefore I can take the differential delta of log W will be equal to, remember only Ni is okay, the variable. So that is sum over I. For the first case, there will be only delta Ni, first term log Gi. Log Gi is a constant, minus, for the second term we have to do both. Okay, that is I can say Ni into delta Ni divided by Ni. For the log it becomes like that, minus we can say delta Ni log of Ni. For the first term it is over, then what, plus delta Ni. So you know what is going to happen over here. This Ni and Ni will be getting cancelled. So minus delta Ni and this plus delta Ni will be getting cancelled over. So finally you are left with a simplification, that is sum over I as usual. Then you can take a delta Ni as common term out of the two terms. So it will be log A minus B form. So that will be log of Gi divided by Ni whole multiplied by delta Ni. So we call that, this is equation number 2. Okay, now for the most probable distribution set, okay, so for the most probable distribution, you know, we have to maximize it obeying the constraints. Most probable distribution set, okay, what do you have to do? We have to use the Lagrange's method. So that is delta log W. By the time I think you are quite familiar with the technique, sum over I first constraint equation delta Ni, okay, then minus beta into sum over I Ei delta Ni. The two constraints are included by alpha and beta equal to 0, set equal to 0. So on substituting equation number 2 here for delta Ni, you will be getting, so that is sum over I log of Gi by, so instead of Ni we can call it as Ni star to denote the most probable distribution, minus alpha minus beta Ei, okay, and delta Ni is also common factor there, that is equal to 0. And the direct consequence will be that log of, you know, okay, see that quantity in the bracket should be equal to 0, so which says that log of Gi divided by the Maxell Boltzmann case becomes straightforward, that should be equal to simply alpha plus beta Ei only. There is no plus or minus 1 or anything there, but I need Gi by Ni star, so that is Gi by Ni star will be equal to simply e raised to alpha plus beta Ei, or we are in need of the mean occupation number, which is nothing but the reciprocal of the LHS, that is Ni star by Gi. For the, okay, what is that, the Maxell Boltzmann case, that will be simply equal to 1 divided by e raised to alpha plus beta Ei, which is nothing but what we call as the Maxell Boltzmann distribution function f of mb, which is also nothing but the mean occupation number for the Maxell Boltzmann case. So this is the Maxell Boltzmann distribution function, which gives the mean occupation number of a level for a classical case. So this is the final equation to be remembered. Now I think we are in a position to finally just compare all the three distribution functions. So in general, we can just summarize it like this. In general, we can say ni star by gi, which is nothing but notated as f of ei is equal to, we can say this is equal to 1 divided by e raised to alpha plus beta ei plus a. So we can write just plus a, where when a is equal to minus 1, we get the Bose-Einstein case. When a is equal to plus 1, we get the Fermi-Dirac case. And when finally a equal to 0, we get the classical case, which is what? The Maxell Boltzmann case. So just by remembering the single equation, all the three distribution functions can be compared and memorized easily. So that's about the derivation of the three distribution functions. Okay. So by that, I think the major topics of distribution functions are over, and now we'll be in a state to individually discuss the ideal Bose systems and ideal Fermi systems, which are given us two separate modules. So I'll be discussing the ideal Bose systems in the next lecture onwards. For that, actually we need some starting points which are given in ideal gas in canonical and grand canonical ensemble topic, which we are not doing. Okay, it's comparatively not that much relevant, but I'm taking the results to save time. അപ്പോൾ നമ്മൾ ഇപ്പോൾ കണ്ടത് ക്വാണ്ടം മെക്കാനിക്കൽ മൈക്രോ കനോണിക്കൽ എൻസെമ്പിളുള്ള റിസൾട്ടാണ്. ഓക്കെ, അതുപോലെ തന്നെ നമുക്ക് വേണമെങ്കിൽ ഐഡിയൽ ഗ്യാസിനെ കനോണിക്കലിലും ഗ്രാൻഡ് കനോണിക്കൽ എൻസെമ്പിളുടെയും മെമ്പേഴ്സായിട്ടൊക്കെ എടുത്തിട്ടുണ്ട് എങ്കിൽ നമുക്ക് അവിടെ ക്യൂ പൊട്ടൻഷ്യലാണ് വരിക. നമുക്കറിയാം ഗ്രാൻഡ് കനോണിക്കൽ എൻസെമ്പിളിൽ നമ്മൾ ക്യൂ പൊട്ടൻഷ്യൽ ഡിഫൈൻ ചെയ്തു. ഓക്കെ, അപ്പോൾ ആ ക്യൂ പൊട്ടൻഷ്യൽ ഓഫ് ദ സിസ്റ്റം ഡെറൈവ് ചെയ്തെടുക്കാൻ പറ്റും. ഞാൻ ആ ക്യൂ പൊട്ടൻഷ്യൽ നേരിട്ട് തരികയാണ് ആസ് എ നോട്ട്. ഓക്കെ, സോ ഫോർ ദ നോട്ട് യു ക്യാൻ റെഫർ ടു പെത്രിയ ഓർ MCT notes for getting okay these derivations if time permits. Okay, so it can be shown that, so we will just start from here. It can be shown that the Q potential of the system, Q potential is log z എന്ന് ഓർമ്മയുണ്ടാവും of the system is given by Q is equal to, Q is actually, you remember, Q is a function of fugacity Z, volume V and temperature T. Fugacity Z ഓർമ്മയുണ്ടാവും, നമ്മൾ കെമിക്കൽ പൊട്ടൻഷ്യൽ പകരമായിട്ട് കൊണ്ടുവന്നതാണ് fugacity. Q of ZVT is equal to, generally നമുക്ക് ഇങ്ങനെ എഴുതാം, 1/A into summation over all energy values log of 1 plus A Z e raised to minus beta e. ഇതാണ് ഒരു ഇക്വേഷൻ. ഇവിടെ where A is equal to -1 for നമ്മൾ നേരത്തെ പറഞ്ഞ പോലെ തന്നെ Bose-Einstein case, and A is equal to +1 for Fermi-Dirac case. അപ്പോൾ നമുക്ക് രണ്ട് കേസുകളും ഈ ഒരൊറ്റ ഇക്വേഷൻ കൊണ്ട് തന്നെ സൂചിപ്പിക്കാൻ പറ്റും. ഓക്കെ, and of course you know z is equal to this z, small z is equal to fugacity e raised to minus alpha. Alpha is equal to mu minus mu by kt, so it will become e raised to mu by plus mu by kt, where mu is the chemical potential of the system. Okay, so therefore we can conclude that therefore this is the beginning equation that we'll be using for ideal Fermi and Bose systems. We will please memorize equation number 1. So therefore Q is equal to minus, okay, A is equal to -1, so it will be equal to minus of sum over energy values, okay, log 1 plus, I'm sorry, A equal to -1, that is 1, sorry, A equal to minus, no, so it will be 1 minus, yes, of course, so it is 1 minus Z e raised to minus beta e, okay, 1 minus Z e raised to minus beta e for Bose ideal Bose systems or Bose-Einstein systems, and Q is equal to plus, that is sum over E log of 1 plus Z e raised to minus beta E as far as the Fermi-Dirac systems are concerned. Okay, so these results, or say, please memorize equation number 1, which will be used for the discussion of the next two modules. That will be the starting point of our discussion there. So this module, almost the main topics are covered. So you can just focus on the derivation of the three distribution functions. Please practice it well. Remember its relevance also. We'll be using that result also later. Okay. So for the derivation of equation number 1 here, refer Petria, Statistical Mechanics by Petria, whose soft copy has already been uploaded for derivation. Okay, for derivation. So that derivation can be just done. It's a bit lengthy, but we need only this result. That's all regarding the module. Thank you.